Imagine a ship nearly 4 football fields long moving between dunes, sand, and barren shores. From a distance, it looks as though someone placed an ocean giant in the wrong place. There is no open horizon, no towering waves, and no room to change direction. Only a ribbon of water, narrow beside the massive hull, cutting through one of the driest landscapes on Earth. How can a vessel built to cross oceans navigate through the middle of a desert? Welcome to Invisible Structures. Today, we will explore the engineering that turned dry land into a maritime highway and discover why this passage must be rebuilt, corrected, and monitored every single day. The Suez Canal connects the Mediterranean Sea to the Red Sea through Egypt. In its modern configuration, it stretches roughly 193 kilometers and symbolically separates Africa from Asia, placing the Sinai Peninsula on the Asian side. On a map, it is only a thin line, but that line is wide enough to reshape global trade and narrow enough to become a crisis when something goes wrong. Seen from water level, that thin line becomes an enormous corridor filled with ships carrying thousands of containers. The scene feels unnatural because a ship this large normally depends on open space. It takes time to accelerate, even longer to stop, and cannot make a sudden turn. In Suez, all that mass must follow a fixed path, with nearby banks, controlled depth, and almost no freedom to improvise. The canal also deceives the eye. Its calm surface makes the crossing look simple, as though a ship only needs to point its bow forward and continue. But that calm is an illusion. The systems keeping the hull safely in motion are hidden below the water, within reinforced banks, depth charts, dredgers, pilots, and traffic control rooms. Before we continue, subscribe to Invisible Structures and consider this question. If this waterway was carved through the desert, what keeps sand, sediment, unstable banks, and giant ships from closing it again? To find the answer, we must return to a time when all of this was still an almost absurd idea. Cutting across Egypt to unite 2 seas. The desire to connect the Mediterranean to the Red Sea is far older than the modern canal. Long before massive container ships, rulers of ancient Egypt were already trying to create navigable routes between the Nile, the Bitter Lakes, and the Red Sea. But those ancient waterways were not the Suez Canal we know today. They followed different routes, depended on the river, and were abandoned, buried, or reopened at different times. Still, they revealed an ancient obsession, turning Egypt into a gateway between worlds. The sand had already revealed a rule that remains true today. In the desert, an excavated passage does not stay open on its own. It exists only as long as someone can defend it. Centuries later, during the French campaign in Egypt, the possibility of opening a direct connection was studied again. Engineers from Napoleon's expedition concluded that the Red Sea stood about 9 meters above the Mediterranean. If true, cutting through the isthmus could unleash a dangerous current and require structures to control the water. The measurement was wrong. The water levels were close enough to allow a sea-level canal. Even so, the mistake helped delay the project for decades. Before confronting sand, mud, and heat, Suez was nearly defeated by incorrect numbers. In the 19th century, Ferdinand de Lesseps secured the concession to organize the company responsible for the canal. Excavation began on April the 25th, 1859. The line drawn on a map had to become one continuous cut through vastly different terrain. During the first years, much of the work depended on immense human effort. Laborers dug trenches and removed soil before dredgers, and mechanical excavators took over larger portions of the operation. Creating a depression was not enough. They needed a corridor deep and wide enough to carry ships. Construction lasted nearly 10 years. According to the Canal Authority's historical records, roughly 74 million cubic meters of material were removed. In August of 1869, the waters from both sides met. On November 17th, the route opened with an international procession of ships. But that canal was very different from the one we see today. It was shorter, its navigable channel was narrow, and its maximum depth at opening was approximately 8 meters. Ships were smaller as well. Without repeated expansions, the structure built in 1869 could not accommodate many of the giants now crossing Suez. The canal grew alongside the shipping industry. As vessels became wider, heavier, and deeper, the bottom had to descend. As traffic increased, sections were widened or duplicated. Curves were redesigned, and passing areas were expanded. In the modern configuration reported by the Suez Canal Authority, the depth reached 24 meters. Much of the corridor we see today is the result of more than a century of excavation, deepening, widening, and correction. The moment the machines completed the original passage, another battle began. Building Suez was a monumental victory. Keeping it open would become an endless task. Beneath every ship lies a distance almost no one sees, the clearance between the hull and the bottom. For a freighter hundreds of meters long and weighing thousands of tons, that margin determines whether the voyage continues or ends with steel trapped in sand. The desert does not need to swallow all of Suez to threaten the crossing. It only needs to reduce the depth by a few meters in the wrong place. Draft is the depth of a ship below the waterline. The heavier the cargo, the deeper the hull sinks. Operators must compare that draft with the available depth along every section. The canal bottom cannot be treated like a forgotten floor. It must remain within a carefully controlled profile. That is where dredgers enter, the machines performing Suez's most important and least visible work. They are engineering's daily response to a bottom that refuses to stay still. Some cut through compacted material. Others suction a mixture of water, sand, and mud. The removed material travels through pipelines, is deposited in designated areas, or is used for land reclamation and reinforcement. The principle sounds simple. Remove whatever has accumulated. In practice, it is a continuous operation of measurement and correction. The desert does not attack all at once. It advances through particles, sediment, and tiny changes that seem insignificant until they begin eroding the safety margin. The canal crosses different soils, collects sediment, and endures the force of enormous ships. Displaced water generates waves and pressure against the sides. That is why the banks are armored with stone and, in some locations, metal structures that resist erosion and instability. The walls are not vertical. They form slopes calculated for each type of soil. If a bank loses material, the navigable section changes. If the bottom rises, clearance beneath the hull shrinks. Teams conduct hydrographic surveys, track depths, and send dredgers wherever intervention is needed. Suez looks motionless on a map, but its true shape is constantly being verified. This work became especially visible during the expansion inaugurated in 2015. The project combined a new parallel section with the deepening and widening of existing stretches, totaling 72 kilometers of work. 45 dredgers were deployed, removing 258.8 million cubic meters of material. Imagine removing the contents of tens of thousands of Olympic swimming pools, so a line of ships can keep moving through the desert. Every cubic meter removed creates space, restores depth, or prepares a new navigable section. This is the canal's invisible mechanism. It does not defeat the terrain once. It defeats it through maintenance. If this hidden engineering is surprising you, leave a like. It helps invisible structures reveal the operations concealed behind the greatest structures on Earth. Dredging also follows the evolution of ships. A corridor suited to freighters from another era can become restrictive for wider, deeper vessels. Expanding Suez requires calculating slopes, protecting banks, repositioning buoys, adapting waiting areas, and testing the new geometry under real traffic conditions. Even the water displaced by the hull demands attention. When a ship occupies much of a restricted channel, the water must escape along the sides and underneath. That flow changes the pressure around the vessel. That is why width and depth influence how a ship behaves. A protected bank prevents material loss. A dredged bottom preserves clearance. A redesigned curve reduces sudden corrections. A duplicated section helps separate opposing traffic. Maintenance must also coexist with navigation. The canal cannot shut down every time a dredger works. Locations, schedules, and sections are planned so machines and commercial vessels can share the system. It is like a linear factory nearly 200 kilometers long, and its product is passage. When a cruise ship glides calmly between the banks, it is sailing above millions of cubic meters of removed material, depth surveys, and protective layers holding the terrain in place. The crossing looks natural only because maintenance erases every sign of the battle. But sufficient depth does not guarantee safety. After creating room for the giants, the most delicate task remains: guiding them through a narrow, slow, controlled corridor without allowing the shortcut to become a blockade. In the open ocean, a ship has room to correct its course. In Suez, it does not. It must remain inside a narrow navigable lane while respecting speed, depth, and a tightly coordinated operation. Ships cross in convoys, with northbound and southbound traffic organized by schedule. No vessel enters whenever it chooses, because improvised encounters between giant hulls could turn the crossing into chaos. Before entering, the ship's dimensions, cargo, draft, and condition are evaluated. Pilots familiar with the canal board to assist with navigation. They know the curves, landmarks, passing areas, and expected behavior in each section. The captain remains responsible, but the pilot reduces uncertainty in a place where only a few meters can make all the difference. Speed is controlled. Moving too fast increases wave energy against the banks, reduces reaction time, and intensifies hydrodynamic effects. Moving too slowly can disrupt traffic. The crossing demands balance. In duplicated sections, opposing traffic can move more freely. Elsewhere, the sequence must be carefully organized. The Great Bitter Lake serves as an important coordination and passing area. The result is a journey lasting many hours, even though the distance seems small compared with an ocean crossing. Now, imagine the bridge of a container ship. The bow is so far away that small changes in angle take time to become visible. Wind strikes the rows of containers as though pushing against a wall. The rudder must redirect a massive body that continues moving through inertia. The larger the ship, the earlier a correction must begin. By the time a deviation becomes obvious, the hull may have already built up too much sideways momentum. Tugboats remain available for assistance and emergencies. Buoys, electronic charts, and constant communication help keep every vessel inside the corridor. One word reveals how Suez shapes decisions made far beyond Egypt. Suezmax. The term describes the limits for ships designed to pass through the canal, especially their dimensions and draft. The structure does not merely receive vessels, it helps determine what shipyards and shipping companies build. In March of 2021, the risk stopped being hypothetical. The Ever Given, a container ship roughly 400 meters long, ran aground in a single-lane section and turned diagonally across the canal. Its bow became lodged in one bank, blocking the entire passage for 6 days. To free the ship, crews combined tugboats, dredging near the bow, and assistance from the tides. The image exposed a brutal truth. A structure that brings continents closer can be stopped by a few degrees in the angle of a single ship. The Ever Given lost its safety margin inside a restricted corridor. In the ocean, it would have had more room to drift and recover. In Suez, the bank became an obstacle. The blockage also showed that dredgers protect safety, not just depth. During the salvage operation, removing sand near the hull helped release the bow. The machine that preserves the canal each day became a decisive tool in a global emergency. After the incident, expansion work in the southern sector was increased to improve safety and capacity in critical sections. History repeated itself. Larger ships and newly exposed weaknesses demanded further adaptation. Tell me in the comments, what impresses you most about Suez? The non-stop dredging or the control required to guide these giants? Suez removes freedom from ships and replaces it with coordination. Schedules, pilots, speed, distance, depth, and tugboats all become part of one unified operation. But why do so many countries and companies feel the impact when this strip of water stops working? The answer lies in the route ships must follow without it. To understand the value of Suez, erase that line from the map for a moment. Without it, many ships traveling between Asia and Europe must circle southern Africa around the Cape of Good Hope, adding thousands of kilometers and days to the journey. More distance means more fuel, more crew days, more wear, and fewer possible voyages for each ship. That is how a physical structure in Egypt makes the world smaller. It does not move continents closer. It eliminates an enormous detour. That impact became clear when insecurity in the Red Sea drove many companies away from the route. The canal remained physically open, but part of its function disappeared. Ships no longer trusted the path leading to it. A structure can remain intact, yet lose part of its purpose when the surrounding region becomes unreliable. Suez depends on dredging, stable banks, and internal control, but its usefulness also depends on ships being able to reach both ends. Its advantage comes from geometry. An artificial line through the desert replaces the voyage around an entire continent. And that line cannot sustain itself. The bottom must preserve enough depth for each ship's draft. The banks must resist waves and pressure from passing hulls. The slopes must hold their shape. Pilots and controllers organize convoys. Tugboats remain ready. Dredgers remove the material that narrows the passage. That is why Suez is not merely a water-filled trench or a shortcut opened in the 19th century. It is a machine built across the landscape, with components spread over nearly 200 kilometers. When everything works, we see only a ship moving slowly through the desert. That apparent simplicity means the bottom is at the correct depth, the banks remain stable, and the convoy is synchronized. In Panama, structures raise and lower ships. In Suez, the spectacle is less visible. Engineering keeps a waterway open through the desert, so the world does not have to sail around Africa. To discover more structures that quietly support the world beyond our sight, subscribe to Invisible Structures. And tell us in the comments which detail changed how you see Suez. Its construction, the dredging, the controlled crossing, or the sheer scale of the corridor. The Suez Canal is not a line opened once and left behind. It is a passage engineering must conquer again every single day.